So, the next one is using the Gauss's law for charges. So, we again take a pill box, okay, a pill box with an area A and a height h. Okay. Now, this is the volume that I am considering. Let us say we have our epsilon 1, mu 1, sigma 1, region 1 at the bottom, epsilon 2, mu 2, sigma 2 on the top. So, we also allow for sheet charges to be present, right, because sigma 1 or sigma 2 can be non-zero, right, in which case there can be surface charges present, right. If they were perfect dielectrics, there would be no surface charges. Okay. In this case, it is actually beneficial to work with the displacement vector, d vector. We call this d normal and d tangential. Okay. So, let us recall the Maxwell's equation. The volume that encompasses has a certain closed surface, right. So, the closed surface integral of d dot dA is the volume integral of rho times dV. So, we are considering a volume that is contained in this pill box, which could have a certain charge density rho. So, the net integrated charge that is within this volume is equal to the surface integral of the displacement vector on the outer side of the volume, right. So, if I take a dA on the surface of the pill box, it should be normal to the surface, right, and d normal is going to be aligned with this dA vector, right. So, so the trick here that we are going to do to get the boundary condition is, remember that we are going to make h arbitrarily small, right. So, in the limit h tends to 0, right, the contribution from the surface integral from the sides of the cylinder, the curved surface of the cylinder, is going to vanish, right. So, we will only be interested in the surface integral contribution that comes from the top and the bottom flat surfaces, circular surfaces, right. So, we can write that as d n 2 times A minus d n 1 times A, and remember, if there is only sheet charges, right, this integral of rho dV just becomes rho s times A, right. I have a certain sheet charge density that multiplied by the area gives me the net charge that is contained within the pill box, right. So, the A's cancel and we get our second boundary condition using the displacement vector dn2 minus dn1 is the surface charges. Second boundary condition, and this of course can be generalized to saying that n cap dot dn, sorry, d2 minus n cap dot d1 is equal to rho s. So remember, the n cap is in this direction. Okay, so we are asking the question, how much of the d vector is aligned towards the normal vector of the interface, right? Alright, so there is a small correction, it is n dot d1 minus n dot d2, right, because our n cap is facing in the downward direction. We are asking how much of the d vector is facing down, right, and n cap is opposite to the direction of my dA vector, right. So just verify this, that it should be n dot d1 minus n dot d2 is rho s, right. So the third boundary condition is just a follow up from our prior work with charges, since the magnetic charges are 0, right. So we are just going to invoke the Gauss's law for magnetic fields, and here we know that the closed loop surface integral B dot dA is 0, right, because there are no magnetic charges. This essentially would give us Bn2 minus Bn1 is equal to 0, right. Or n dot B1 minus n dot B2 is equal to 0. This is our third boundary condition. Okay, so this is a simple one, right. So taking the same pillbox from the previous slide, since there are no magnetic charges, we essentially find that the normal component of the B field, right, which is the magnetic flux density, right. If I were to change this to the magnetic field intensity H, right, remember that you would have mu2 H2 Hn, right. So if you want to write this in H, it would be mu1 H normal 1 is equal to mu2 H normal 2. Okay. So please ensure that you are comfortable going back and forth between B and H or E and D, right. Okay. The last of the boundary conditions comes from the Ampere-Maxwell's equation, right. So in the integral form, it is H dot ds is the surface integral J dot dA plus epsilon integral dou E by dou T dot dA, right, or I can also write this as using the displacement vector d. Okay, so we are going to do the same exercise. Like in the case of the Maxwell's equation from Faraday's law, right? we are going to take a closed contour right, and there can be volume currents and surface currents. Okay, so I'll call this volume current density J, and the one that's drawn at the interface as a surface current density. Okay, so this loop can contain both. Okay, and let's define the two media. So I have my medium 1 on the top and medium 2 at the bottom. Okay, and my n vector is going from medium 2 to medium 1. Okay, so we are going to do the same trick. This width W, which we considered, in this case h, I am just going to shrink that to 0, right, in which case the line integral contribution from that is going to vanish, right. So let's look at the line integral, closed loop line integral h dot ds. It quite simply becomes the h tangential 1 times, let's say, L. Okay, let's take this as L. So in the limit h tends to 0, ht1L minus ht2L. Remember, the contributions from the side that is length h, right, is going to vanish. So I am not including that here. This is the left hand side, and the right hand side, remember, as this loop shrinks, the only thing that will survive is the surface current, right. So the volume current, so the surface current becomes Js times L, right, that gives us the current enclosed, whereas the limit h tends to 0, J times LH, this is going to go to 0, right, and similarly the electrical flux is also going to go to 0. So dou D perpendicular by dou T times LH, right. So just like in the case for our magnetic flux, even the flux due to the displacement vector and the volume current contributions, they vanish, right. So all that's left is to say that ht1 minus ht2 is equal to Js. Of course, I have considered the contour to be perpendicular to the direction in which the surface current is flowing locally, right. That just makes these convenient. Okay. And you can also remember, right, from your Biot-Savart's law, that if I have a current going into the plane, right, the fingers show me the direction of the magnetic field that's circulating around this current carrying wire, right. So if I have my currents flowing into the surface of the screen demarcated by the X and the circle, right, I would expect the magnetic fields to be circling around in the contour in the direction shown by the blue arrows, right, along the contour. right. So, in this particular boundary condition, the last and the final boundary condition we have, it is important to remember, right. So, remember H and J, right, HT and J are not in the same direction, JS are not in the same direction. Okay, please keep this in mind, okay, because even if I were to give you situations where there are surface currents, you should know that the direction of the magnetic field would have to be dictated by the Biot-Savart's law, right. So, we can generalize this into N cross H1 minus H2 is equal to Js, becomes a vector equation. Okay. The reason I am able to extend this from the tangential component to the full vector is because n cross H normal is identically 0, because the cross product of two vectors that are collinear, right, is 0. So, since that is 0, I can extend the relationship to the cross product of the unit normal vector at the interface and the difference of the magnetic fields, right, gives us the flow of the surface currents. Okay. So, this summarizes all the boundary conditions that we get from the 4 Maxwell's equations. These are going to be an integral part in trying to estimate what happens to a plane wave when incident at a boundary. Okay. We are going to invoke all these relations in order to estimate what the reflection coefficients and the transmission coefficients are at the interface. So, just to summarize, if I had, say, a perfect dielectric to a perfect dielectric interface, right. So, in this case sigma 1 and sigma 2 is 0, right. So, if I have a perfect dielectric on either side of the interface, but their epsilons and mu values are different, we can say that rho s and Js are 0 in these, right. So, we can say rho s and Js is 0. So, the boundary conditions quite simply become okay. Since surface charges and surface currents are 0, it becomes just an equality, right. So, kind of reminds you of the equality that we took for the voltages and currents in the transmission line on either side of the termination. So, in the case of a dielectric and a perfect conductor, so what you were taught in high school about perfect conductors is there can be no fields, electric or magnetic fields inside a perfect conductor, right. So, which means that all the corresponding field values in medium 2, right, assuming medium 2 is the perfect conductor, will all be 0, right. So, let us relook, but remember that conductors can allow for surface charges and surface currents, right. So we have ET1 is simply 0. So we cannot have electric fields that are not perpendicular to a perfect conductor, right. So we can have no component of the electric field, right, along the plane of the perfect conductor, okay. And then the normal displacement vector is simply the surface charge. Similarly, the tangential component of the magnetic field is the surface current, and the normal component of B field is 0. Okay. So with this, let us conclude our discussions on boundary conditions. Please take a look at this carefully, because we are going to use these results for our derivations of interaction of a plane wave with interfaces. Thank you.